Hello, grade 12s. In this video, we are going to be using our knowledge of the structure of the atom and valence electrons to be able to predict and to draw ionic and covalent bonding and explain what's going on. So ionic bonds happen because atoms form ions. One atom becomes positive because it's lost electrons, like the sodium will lose its one valence electron in the 3s sublevel. The other becomes negative because it gains one. We have chlorine will gain one electron into its 3p sublevel. So the sodium becomes a positive ion, the chlorine becomes a negative ion, and they become electrostatically attached to each other, so opposites attract. And this forms an ionic bond between the two atoms, now ions. When we draw ionic bonding, I always want us to use square brackets and to indicate the charge. So for example, to draw the ionic bond between magnesium and bromine, we know magnesium has 2 valence electrons, and bromine, being in group 7, will have 7. Magnesium will give away its 2 valence electrons, and so it will become a magnesium plus 2 ion. Bromine can gain 1. Magnesium can give 1 electron to each bromine. Magnesium will need a second bromine in order to fully give away all of its electrons. So we are going to need 2 of the now bromide ions, which will now have a charge of -1 because they have gained their electrons. I suppose it would be more correct to keep this little brackets to keep my charge outside the brackets. So anytime we have ionic bonding, I want us to make sure that we use these square brackets and show the charge. Ionic bonds happen typically between metals and non-metals. Covalent bonding involves sharing electrons. When we have covalent bonding, it's typically going to happen between 2 nonmetals or between hydrogen and nonmetals. Covalently bonded compounds are commonly called molecules. So covalent bonding happens because neither atom is strong enough to actually remove the electron from the neighboring atom, and so they end up sharing. In the case of diatomic hydrogen, each hydrogen in its valence shell has 1 electron. So another hydrogen shares his own electron. From the point of view of each hydrogen, their outer shell is full, as hydrogen and helium have a complete outer shell with only 2 electrons. In the case of oxygen, I've drawn here the orbital diagrams for 2 different oxygen atoms. We fill in 1s for 2, 2s for 2, and 2p for 4. You notice that in the second energy level, in the p sublevel, there are 2 unpaired electrons. So there are 2 sites available for bonding. That orbital shares with another oxygen because they have identical electronegativities. And so each oxygen will share in 2 separate places and form a double bond. We can see that happening here. Covalent bonding can also happen between 2 different atoms, as in the case of water. How do we tell if a bond will be ionic and covalent? Well, a quick check is we can look at an ionic bond and know that it's typically between a metal plus a nonmetal. Covalent bonding is typically between 2 nonmetals. It'll be a nonmetal and another nonmetal. But we can also check the electronegativities. When we compare the electronegativities of 2 atoms, and we'll hit a point if we subtract. This chart shows 1.9. I've also seen textbooks use 1.67. So anywhere between about 1.7 to 1.9 is the tipping point for ionic bonding. Somewhere in this range is enough of a pull on the electrons to remove the electrons and to have that positive-negative electrostatic attraction and get an ionic bond. Differences in electronegativities less than that amount form covalent, where the electronegativity difference is between 0.5 and about 1.67, it is nonpolar, or it is polar. That is being pulled more strongly by one atom than the other. When the difference in electronegativities is between 0 and 0.5, we will call that nonpolar covalent, and it is an equal sharing of electrons. In a nonpolar covalent bond, the valence electrons are shared equally, and there is no positive or negative side to the molecule. In a polar covalent bond, we have unequal sharing. One side looks a little bit positive, and the other side looks a little bit negative. This is the lowercase letter delta in Greek. It means it looks a little bit. It's not all the way positive and negative. In an ionic bond, we have a sodium, for example, fully giving up an electron and being all the way positive, and the anion gaining electrons and being all the way negative. So the bonding is different between the different types of molecules and compounds that can be formed, and accounts for different characteristics. So to determine bond type, our best difference is to look up the electronegativities, which you can find on your periodic tables that I handed out with the course. Find the difference by subtracting and then compare it to the chart. For our purposes, we will use 1.67 as the cutoff from ionic and covalent. In future classes, you will have different professors offer different values. Use the cutoff value that is recommended for that class. In our class, I won't give any values for you that kind of fall in that judgment zone. Although a good rule of thumb is when you have that gray area, if it's a metal and nonmetal, tend towards ionic, and if it's two nonmetals, tend towards covalent. Molecular compounds are also called covalent compounds. Typically, they happen between two or more nonmetals. I've said for ionic compounds we would use square brackets and show charges, but how do I draw the bonding that happens in covalent compounds? We're going to use Lewis structure diagrams to draw the bonding for covalent compounds. This will help us to eventually be able to predict the shapes of molecules. So we're going to go through a 5-step method to teach us how to draw different molecules based on their Lewis structures. In step 1, we identify the compound as being covalent because it is made up of two or more nonmetals. Both phosphorus and chlorine are nonmetals. I determine the number of valence electrons in the molecule. Phosphorus is in group 5 on the periodic table and has 5 valence electrons. Each chlorine is in group 7 and therefore has 7 valence electrons. We can see from the formula that there are 3 of them. So 7 times 3 gives us 21 valence electrons from the chlorines, plus the 5 valence electrons available from the phosphorus to give us 26 valence electrons in total to work with. Now that we know we have 26 valence electrons to work with, we can start to draw the molecule. We're going to put the atom with the lowest electronegativity in the center and put the remaining atoms around it as terminal atoms. Now, in all fairness, guys, the one that goes in the center is usually the one of a kind. Hydrogen always is terminal, it always goes on the outsides, but usually it's pretty obvious who's going to go in the middle. To attach that central atom to the terminal atoms, we're going to build a bond. And remember that a bond is always 2 electrons. You can draw those 2 electrons as a single pair of dots. You may also choose to draw this as a line, but I find that sometimes when people draw a line, they lose track of how many electrons they've used. At this point, we have used 6 of our 26 available electrons. In step 3, I'm going to use the remaining electrons that I have as outer electrons for those terminal atoms. These are the atoms that had higher electronegativity and will get first dibs at the remaining electrons. So we already had these 6 electrons. Continuing with unbonded pairs, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. We have now used 24 of my available 26 electrons. Step 4 is if you have remaining electrons, add them to your central atom. Once the outer electrons have all been filled, the central atom will take the remainders. At this point, we have used all 26 electrons. And doing a quick check, looking around each atom to see if there are 8 electrons. I see 2, 4, 6, 8 around the chlorine, 2, 4, 6, 8 around this chlorine, and around this one. When I circle the phosphorus, I get 2, 4, 6, 8. There are 3 places where bonds are made between the phosphoruses and the chlorines. These are the shared electron pairs that are involved in the single bonds. Now, I said this was a 5-step method, so let's go to an example where I'd have to use a 5th step. We're going to do the modeling for carbon dioxide. In carbon dioxide, carbon, because it's in group 4, has 4 valence electrons. Both of the oxygens, being from group 6, will have 6 valence electrons. 6 times 2 is 12, plus 4 is 16. Now that we know how many valence electrons we have to use, we start by putting the carbon in the middle and attaching it to an oxygen on either side using a single bond. Some people will draw the same structure like this, with a line representing an electron pair. Again, 2 dots or a line means the same thing. It means a single bond. You are allowed to use either of those as your drawing structure, so long as you remember how many electrons are involved in your bond. The remaining electrons will go to complete the octets on the terminal, except for hydrogen, who of course would be full. So we've already used up 4 of my electrons. The remaining electrons go around each of the oxygens. At this point, we have used up all of my electrons. So step 4 said to put any leftover electrons on the central atom. We don't have any extra electrons. However, checking around each of the atoms, this oxygen has 8 electrons. It has an octet and is stable. This oxygen has 8 electrons. It has an octet and is stable. But the carbon in the center has only 4 electrons. It does not have an octet. So we are not done, and we have a problem. We have no more electrons to give it. What we're going to do is migrate electrons from the oxygens towards the central atom until it also has an octet. We have taken a pair of electrons, one from each of the oxygens, and moved them to the center. You may see it drawn like this, with 4 dots representing a double bond on either side. This may also be drawn as a pair of lines. Checking now to see if we have octets. Oxygen sees 2, 4, 6, 8. This oxygen sees 2, 4, 6, 8. And the central carbon sees 2, 4, 6, 8. Every atom has a full octet surrounding it and is now stable. So when we don't have enough electrons to make the central atom have a completed octet, we will migrate in and make double or even triple bonds. In this formula, we could see that we would need to have a triple bond. Going through the steps quickly with you, we know that we have hydrogen with 1 valence electron, carbon with 4 valence electrons, and nitrogen with 5 valence electrons, which give us a total of 10 electrons to work with. This is a great example of having to decide which element could go as your central atom. We know it can't be hydrogen because hydrogen can only bond on one side. comparing the electronegativities of carbon and nitrogen, and carbon is the least electronegative of the two. It would go in the middle. We would start by attaching the carbon to the hydrogen and to the nitrogen with single bonds. We then use remaining electrons to complete octets. Hydrogen's octet is already full. Adding pairs of electrons around the nitrogen completes its octet. We now have used all 10 electrons. At this point, checking to see whether or not the atoms have completed their octets, hydrogen has and nitrogen has, but carbon does not. To solve the problem that occurs, we migrate pairs of electrons. I take 2 of them from the nitrogen and bring them in and check again. Nitrogen still has 2, 4, 6, 8. But carbon now only has 2, 4, 6. So we'd have to migrate in yet another pair. We'll take one more pair of electrons and migrate that into the center to form the triple bond. Here we see 8 around the nitrogen and the carbon, and hydrogen's happy with 2. We have formed a triple bond. We can also use this same 5-step method to figure out the Lewis structures for several polyatomic ions. Although the polyatomic ion itself gets used in ionic bonding, the bonding within the ion is usually covalent. When we see a minus charge, that means that we have to add electrons. The -1 charge on the iodate ion means we have to add electrons. If we see a positive charge, this means we have to remove electrons. In the case of the ammonium molecule, nitrogen is in group 5 on the periodic table and has 5 valence electrons. Each hydrogen has 1 valence electrons, and there are 4 of them. And the positive charge means we're going to have to remove 1 electron from the total. We're going to have 5 plus 4 minus 1 will give us a total of 8 electrons to do our bonding with. Putting your nitrogen in the middle and surrounding it on all sides equally with hydrogens, we will attach them by using single bonds. At this point, we check to see if we've used all our electrons, and we have, and then we check to see if we've got complete octets. Remember, hydrogen's octet is completed with only 2 electrons. Nitrogen, a quick check, shows that it does indeed have 8 electrons. Because this is a polyatomic ion and could eventually be used in an ionic bonding, we showed square brackets around it and indicate that we are short 1 electron and have a +1 charge. Let's do one more together. Let's do the nitrate ion. In the nitrate ion, from the nitrogen, we have 5 valence electrons. Each oxygen has 6 valence electrons, and there are 3 of them. The -1 means we get to add 1 more electron to the total. We will have 5 electrons plus 18 electrons plus 1 more electron to give us a total of 24 electrons to be used in our bonding. Start by putting the least electronegative in the middle. The central atom will be nitrogen. We're going to surround it equally with oxygens. Attach the oxygens to the nitrogens with single bonds. We've used 6 of the 24 electrons. We have more to go. Complete the octets on the terminal atoms. We have now used all 24 electrons, but a quick check shows that although each oxygen is surrounded by an octet with 8 electrons, the nitrogen is only surrounded by 6. So we will take from any one of the oxygens, and it doesn't matter which, 1 pair of electrons and migrate them into the center. Now everyone has a full octet. Because this is an ion, I will put it into the square brackets. It was possible because of the extra electron, so it has a -1 charge. In your textbook in chapters 7 and 8, you will find lots of practice about ionic and covalent bonding and relating it to their Lewis structures. There is also a worksheet at the end of your blue workbooks called 40S Bonding and Electronegativity Questions with 26 questions to practice these skills.